Okay, welcome back. This is 4.8 now, differentials. Um, for us, the differentials, the way I teach integrals, they'll be important there. Um, in the future, in my opinion, it's Calc 3 that you really need the differentials for. And it's because I believe the definition of the the definition of the derivative is kind of reliant on the differentials. Knowing whether or not something is differentiable um, is dependent on these little differential things kind of disappearing as you take a limit, I believe. It's been a while since I taught that class, but so anyways, they'll be important later on. Um, my goal here isn't to give you a complete understanding of the differentials, but just to kind of introduce you to them. And what the differential is kind of an approximation to a change. Okay, and where do we see approximations? Well, tangent lines can be used to approximate a function. So we saw the derivative as kind of a slope formula. Okay, now we want to use that derivative slope to create a tangent line. We use that tangent line to do approximations to the actual given curve. Okay. So let's sort of create a scenario. We have a curve like this, called the curve f of x. And then at this point here, we have the point c comma f of c. And on top of that, we can consider the tangent line to that curve. We know its slope is f prime of c. Okay. So we can obtain the formula for this tangent line quite easily just by remembering the point slope form of a line. So we want the slope to be f prime of c, and we're using the point c comma f of c. In the formula, y minus y1 equals m times x minus x1. I'm just getting more paper here. Okay, so dumping all this information into here, I'll have y minus f of c equals m, which I'm replacing with f prime of c, times x minus x1, which will be c. So finally then y, which I'm going to call a tangent line t of x, is equal to f prime of c, or it's probably better to write it in this other way. We'll write it f of c plus f prime of c times x minus c. Okay, so in a region, a very small region about this point, so maybe if we kind of carved out a box like this, and then zoomed in on that box, my pen is dying. You would note that the tangent line is kind of a good approximator of the actual function f of x. Okay? The farther you get away from c, though, it becomes worse and worse, of course. But in a small region around here, they're almost exactly the same. So you can almost kind of replace any function that has a derivative with a tangent line if you get close enough to a particular point. So problem 5 has you explore this in a little bit. So use a linear approximation to complete a table. This is an R, not a P. I'm not insane. I did not write APP. P. We have f of x equals sine x and then c is 2. So we're trying to approximate sine of x about this point 2. So we need a tangent line to do that. Let's sort of look at the chart that's given. Okay, so we're looking at points 1.99, 1.999, 2, 2.01, and then 2.1. So we can populate this chart right now using our calculator, just plugging in 1.99 into there. You get 0.9134. Here you get 0.9097. Here's 0.9093. Here is 0.9051, and then 0.8632. Okay. We want to approximate these values with a tangent line approximation, okay, based off of the point c equals 2. So you can do other tangent lines. That, if you want c to be 1.999, this value and this value would be the same. But for us, this value and this value should be the same. Okay, so 0.9093 should be the same. Okay, so we need this formula. So t of x is what we're looking for. And if we just leech off of this information, it should be f of x sine x plus the derivative of f of x, which is cosine of x, but we're evaluating the derivative at this point 2, so cosine of 2 times x minus 2. Okay, so this will be the formula that I'm going to use, and I'm going to input these values into this formula to get approximations. And what you should see happening is close to 2, it'll be an okay approximation, but then as you get farther away, it's not as good. So let's look at 1.999, we get 0.9097. It's exactly the same almost. 0.9051, exactly the same almost. Okay, and then as you get further out, there's differences. 0.8677 here and 0.9135. So there's kind of a pattern with these things. Later on, you'll study Maclaurin polynomials and Taylor polynomials. It's basically just the coefficients are the derivatives. So you'll have this big polynomial with coefficients that are derivatives of the original function. And there's this other junk where you have to divide by factorial expressions, but it's really just a constant factor, which isn't a big deal. Anyways, you can always approximate. So if you get into trouble, you can use a linear approximation to the curve. So long as you're only working in a very small region, these approximations will give you some information. All right, let's move on to the actual differential now. So section 2, the differential. So this is using the difference in the change in the height of the tangent line to approximate the difference in the change of the height of the curve. Okay, so you're approximating the change in y with the with basically the slope, the derivative, dy. So a picture is worth 1,000 words. Let's just look at the picture. I think it's a good way to go. So we're considering c and then c plus change in x, so some further value down the road. And we have our curve here. It's probably not the best one to, crud. Yeah, definitely not a good example. Let's try that again. Okay, this will work a little better for what I want to show. Let's look at this. So here's our function f of x, and there's two sort of differences you can consider. Delta y, which is the total change in height going from here to here. Okay, so the difference between this height and this height is change in y. So we can write that literally. Delta y is equal to the difference between f of c plus change in x and f of c. And that should look very familiar to you. That's just the numerator from the difference quotient, where we first initially defined our derivative. Okay, so there's a delta y, but there's also a dy. Okay, so what is this dy, the differential of y? Well, the dy is the change in height of the tangent line. Okay, so this distance right here, we're going to call dy. And we'll often use this to approximate this value. And you notice as change in x goes to 0, this value and this value get closer and closer together, or at least they should. So dy is the difference between the tangent line evaluated at c plus change in x and the tangent line evaluated at c. Okay, we can get a nicer expression for this value. And ultimately what we're saying is we want to approximate delta y with dy. Okay, so anyways, let's get a nicer expression for this. And we can use our formula from before, this t of x formula. So substituting this into here, what do we have? We have f of c plus change in x plus f prime of c plus change in x. Or rather, we don't want, we're going to have our tangent line located at c. So let me strike that out, try again. So my tangent line, remember in this example, we could kind of locate the tangent line at any x value we want. And in this case, we're putting our tangent line at c. So we're basing the formula for our tangent line off of this point c comma f of c. So our t of x formula is going to be f of c plus f prime of c times x minus c. So let me do that over. I'm plugging c plus change in x into this formula. Okay, so we'll have f of c plus f prime of c times x, which is now c plus change in x, minus c, and then minus t of c. And of course, t of c is just going to be f of c. So you plug c into here, this formula, you get c minus c, which is 0. This term will be gone. You'll just have f of c. So then plus f of c. Sorry, minus f of c. So there's a minus sign here. So this and this are additive opposites. They'll go away. I'll just be left with this expression. C minus c is 0, so I'll just have f prime of c times change in x. So this expression then is kind of an expression for, I guess, the differential of y at c. In general, let's say change in x will always be dx. Okay, we'll we'll just have that definition. The differential of x, change in x is dx. And then dy, or change in x, or change in y, sorry, is going to be f prime of x dx. And this is the differential of y. And then just let me additionally say, change in y, we're going to be approximating that with dy. And change in y we'll say is approximately equal to f prime of x dx. Okay, so let's look at some of the problems in the book that are associated with this issue. Number 8, they want us to compare delta y and the differential of y. Okay. And they give us y is 6 minus 2x squared. X is negative 2, and delta x, which of course is dx, equals 0.1. Okay, so let's get delta y first, the actual change in y, going from negative 2 to negative 1.9. So we'll have f of negative 1.9 minus f of negative 2. So the delta y is the actual difference in the heights of the function going from one point to the next. And this is our starting point. You can think of this as your c value. Okay, so we could plug these values into here. 6 minus 2 times negative 1.9 squared minus 6 minus 2 times negative 2 squared. If you plop that into your calculator, or if you're ambitious, you can do it in your head. 0.78 for our delta y. So now let's look at dy. Dy, so to take the derivative of this, it's f prime dx, right? So f prime is negative 4x, and then times dx. And so let's use our information. In this case, our x value is negative 2, and our dx is 0.1. Okay, so you'll have negative to negative is positive. 2 times 0.1 is 0.2. 0.2 times 4 is 0.8. Okay. And then we see, okay, these are relatively close. Okay, one application is an error propagation. And we can approximate the total error with the differential. Right? So in particular, f of x plus change in x minus f of x, of course, equals our delta y. This will be your exact value or your measurement error. And so this exact value, the delta x is your measurement error. Okay, so somebody working maybe in a machine shop measures something, that would go here. So it would be the I always get this screwed up. Sorry. This is why I rehearse these things. Well, just let me write down what I have so I don't waste any of your time. This is the measured value. And then delta y will be the propagated error. Okay. All right. So maybe let's look at the example in the book, example 3, just so I can iron this out for us before I get in the class and make a mess of it. Example 3. The measured radius of the ball bearing of 0.7 inches is shown in a figure. The measurement is correct to within 0.01 inch. Estimate the propagated error in the volume of the ball bearing. And so we have a ball bearing being measured by some sort of measuring device. The formula for the volume of this ball bearing, of course, is just the formula for the volume of the sphere, 4/3 pi r cubed. They're telling us the measured value of the measured radius of the ball bearing is, the radius of it is 0.7 inches. And that the measurement is correct to 0.01 inch. Okay, so this is the measured radius. And then there's this delta r, which is in between 0.01 and negative 0.01. Okay, so this is the possible error. Okay, so we're going to estimate the propagated error, the change in y with the differential. And in particular, in this case, then, we'll go dv is equal to, differentiating this, bring down the 3, so we have 4 pi r squared times dr. Okay. And then it's just a matter of substituting in the values in order to get out an approximation. Okay, so substituting in values, we'll have 4 pi times 0.7 squared times dr, which is this delta r thing here. It should be plus or minus 0.1 rather. Okay. Using a calculator, this is plus or minus 0.06158 inches cubed. They may also ask other things. What else may they ask? Relative error, I guess. So this would just be the propagated error. relative error is going to be the ratio of the differential to the value. Okay, so this would be 4 pi r squared dr all over 4/3 pi r cubed. And simplifying, 4 divided by 4/3 is 4 times 3/4, so that would be 3. The pi's are gone, dr all over r. Substituting in the values, we have then 3 times delta r, which is plus or minus 0.01, all over our r value, which is 0.7. And then this will give us a relative error plus or minus 0.0429. Then if they ask for the percent error, you just multiply that by 100. Okay. So in that case, it would be plus or minus 4.29%. Okay. Yeah, so one thing then we'll have from this that I'll be using when I get to integration is the differential form. So we need this differential form. You kind of already know how to do this. So for example, y equals 2x. So I'd ask you to take the derivative. You go y prime is 2. Right? An equivalent way of writing this, given y equals 2x, you can use the Leibniz notation, which is dy over dx equals 2. But you could also rewrite it by kind of multiplying both sides by dx. Technically, it's not real math to do that, but it'll work in this scenario to give us this differential form. When I was sitting in a library studying the history of math and reading about Newton and Leibniz, and Newton was kind of more in this kind of game. He would want to know the relationship between the change in y and the change in x. So you could see it clearly in this formula. The change in the height is twice the change in the x value. So as you move in this direction in x, the height is going up by 2 for every one movement in x. It's the slope formula. Yeah. Leibniz looked at it in this form, though, and I guess the difference between this form and this form is this form you don't necessarily have to let dx go to 0. So if you're taking a limit and thinking in terms of the limit of a difference quotient, here you would not have that issue. You could always let dx go to 0, and you wouldn't be dividing by 0, so you kind of escape that issue. This thing, though, is the differential form. What I'm saying here now is, you may not understand the background of the differential, or maybe even the differential itself. As long as you know how to take the derivative, you can get this form. Okay? And it's kind of just a matter of multiplying both sides by dx. So another example then, y equals 3x cubed. We could say that's the same as dy over dx equals 9x squared, but we can also rewrite it by moving the dx to the other side, which is, you could think of it as multiplying both sides by dx, right? So you'd end up with dy equals 9x squared dx. Okay, so this will be the differential form. For example, number 13, we have y is x tan x. I want the differential form. So dy over dx is just going to be, I'll leave x alone, the derivative of tan is secant squared. plus then the derivative of x is 1, leave tan x alone. And then just move the dx over to the other side. So dy is equal to x secant squared x plus tan x times dx. This form of the derivative I'll be using once I get to the integral section. And I think maybe I teach, sometimes my teaching of the integrals looks a little different, but I'm using these differential forms. So we'll be coming sort of back to this issue in chapter 5. In the meantime, we can use this to kind of pull off parlor tricks. For example, number 42, figuring out the cube root of 26. Okay. So I think to myself, well, I know the cube root of 27, right? And so long as you know the cube root of something close to the value you're trying to find the cube root of, you can do an approximation of the cube root. So the cube root of 27 I know is just 3, right? So the cube root of 26 I can rewrite as f of x minus x plus change in x, right? X plus change in x, and I know that minus f of x can be approximated with the differential dy. In other words, f of x plus change in x is approximately dy minus plus f of x. And so if we allow our x to be 27, I can say this is f of 27 plus a change in x, which in this case, to move it to 26, I'd have to move it by -1. This will be approximately equal to the differential of y. So what is the function I'm dealing with? You can consider it to be the cube root of x. Okay. And then dy will be 1/3 x to the -2/3 dx. And so I just plug my information into this formula. X is 27, so I'll have 1 all over 3 times 27 to the 2/3, and then times the differential of x, which is -1, and then plus f of the particular x value, so plus the cube root of 27, which I know how to do. You can do this all in your head. You don't need a calculator to approximate cube root 26, right? So this is 1 all over 3 times the cube root of 27 is 3, and then 3 squared is 9, and then times -1 plus 3. This will be -1 over 27 plus 81 over 27, which is 80/27ths. Oops. And if you jump to your calculator really quick and figure out the cube root of 26, you're going to see it's pretty close to this value. So it's a neat parlor trick. And you'll see that same kind of trick used later in Calc 3 again. So you'll see it again in Calc 3. Okay, so hopefully that'll get me through my lectures. And thanks for watching.